All right, ladies and gentlemen, we're talking about linear transformations today. So we're going to talk about vertical and horizontal transformations for linear functions. The linear parent function, the first thing we have to talk about before we can talk about any kind of transformation is the parent function. The parent function in this case is the original, it's the original version of the graph. Think about your own parents. They're the original version of you. So the linear parent function for linear equations is f of x is equal to x. And what's really important about this is we need to think about what would this graph actually look like? What is the slope? What is the y-intercept? So if I'm thinking in terms of y equals mx plus b, I want to know my slope. So looking at that x, I want to figure out the coefficient. Well, when a variable is by itself, the coefficient is 1, so my slope is 1. And I can see that I'm not adding anything to it, so my y-intercept is 0. So if I was to graph that line, I would start at 0, 0, and then I would plot some points. I would go up 1 over 1, up 1 over 1. Remember, we're talking about rise over run because our slope is 1. And then I would connect them, and that is the linear parent function. It goes through the origin, and the slope is 1. Now, when we do vertical transformations and horizontal transformations, what we are doing is manipulating this original graph. We're trying to change it around. So the first one we're going to talk about is a vertical shift or a vertical translation. So a vertical shift occurs when something is added or subtracted to the parent function outside of the parentheses. You'll hear me say that over and over and over again. Vertical happens outside of the parentheses. Horizontal happens inside. Think about horizontal. It has an O in the name and it is on the inside. So, the O happens to do with the fact that horizontal is opposite. So it is on the inside horizontal, vertical is on the outside. So the linear parent function, as I said, is f of x is equal to x. We know what that graph looks like. It goes through the origin up 1 over 1. So that's our original parent function, the one in black. Here, I'm giving you g of x is equal to f of x plus 3. Well, over here, I told you f of x is equal to x, so I can just substitute x in for f of x. And so what that means is I've got a slope of 1 still, right? But my y-intercept is 3. So if I was to graph this line, it would be a parallel line just up at 3. Remember, I just took this original graph in black and I dragged it up here to be the one in yellow. So when we talk about vertical transformations, and this will become really important later, vertical transformations are normal ways of thinking. So if I'm adding 3 here, well, when I'm adding in vertical, I move up. So a vertical translation where I'm adding 3, I just moved up 3. The next thing I want to talk about is a vertical stretch. And the best way to think about a stretch is you're pulling the graph so that it gets steeper and longer. A vertical stretch occurs when you multiply the parent function by a number greater than 1 outside of the parentheses. Okay, so remember our linear parent function is f of x is equal to x. So here's our parent function, same one we had last time. This time I have g of x is equal to 2 times f of x. Well, we just said f of x is equal to x, so I could literally take x and I plug it in for f of x. And now if I'm in the mindset of y equals mx plus b, well, I have no b that I'm adding, so the y-intercept is still 0. But this time, if I look at m, my slope is 2, so this means I'm going to go up 2 over 1 when I graph it. So again, starting at 0, 0, but I rose 2, went over 1, rose 2, went over 1. So this stretch, the green graph, I made it steeper than the original black graph. All I did was stretch it. You pulled the ends of the graph so it got wider or taller. A vertical compression, on the other hand, think about compression. When you press something down, you're making it flatter. So vertical compressions happen when you multiply the parent function by a number between 0 and 1 outside of the parentheses. And what it's going to do is I'm going to push that graph down so it's a little bit flatter. Again, our linear parent function is f of x is equal to x. We know what that graph looks like. But this time, I'm still multiplying outside of the parentheses. Remember, vertical is always outside of the parentheses. But I'm multiplying by a fraction or a decimal, something between 0 and 1. Well, I said 1/4 times f of x. We talked about it in the previous examples. F of x is just equal to x. I plug in x, and so I get 1/4 x. So if I start thinking about this in terms of y equals mx plus b, I see that I'm not adding anything to it. So my b is equal to 0. My y-intercept is still 0. But this time my slope has changed to be 1/4 x. So when I graph that, that means I'm going to go up 1 over 4. So here I still go through 0, but I go rise 1, run 4. Rise 1, run 4. And as you can see, that blue line has just been pushed down from the black line. It's a lot flatter. So a vertical compression, we're flattening it. A vertical stretch, we're making it larger. All right, a reflection over the x-axis. This is really the last vertical transformation we're going to talk about. A reflection over the x-axis occurs when we are multiplying by a negative outside the parentheses. And what I will say about reflections is whenever you see a negative, that only deals with the reflection. It doesn't change when I'm talking about the number for the stretch or the compression. So after I've decided there's a reflection, I can basically cover up that negative sign and then look at the number to determine whether it's a stretch or a compression. So here, linear parent function is f of x is equal to x. We know what that graph looks like. It goes straight through the origin. It has a slope of 1. And this time, g of x is equal to negative f of x. So if I change f of x out for x, this is g of x is equal to a negative x. Again, my origin is still the y-intercept, but this time, instead of having a slope of 1, I have a slope of negative 1. So when I graph it, it's going to go down 1, right 1. So as we can see, the blue line's going the opposite way. I go down 1, right 1, down 1, right 1, so that it is a negative slope or negative 1. But if I was to look at this and I look at the x-axis, these two are mirror images of each other. It's completely opposite, completely symmetrical on either side. So when the negative is outside parentheses, you have a reflection over the x-axis. Now let's talk about horizontal transformation versus vertical transformations. This is where it gets a little bit difficult and a little bit confusing. So we need to keep these in our minds. First things first, vertical transformations are always outside of the parentheses. We just saw a whole bunch of vertical transformations and everything was happening outside of the parentheses. Horizontal transformations, on the other hand, which we'll talk about in just a second, are always inside of the parentheses. Always, always, always. And vertical transformations, they operate intuitively, meaning you're thinking in the normal mindset. We talked about that with the vertical translation. Normally, when I add 3 vertically, I move up 3, and that's exactly what I did. But when I talk about a horizontal transformation, they operate typically the opposite way we would normally think. So horizontal, it's got an O in it. We think opposite, horizontal opposite. So let's talk about the horizontal shift or a horizontal translation. So a horizontal shift occurs when something is added or subtracted from the parent function not outside, definitely inside of the parentheses. My mistake. Horizontal is always going to be inside of the parentheses. Go back. Horizontal shift happens inside of the parentheses. So when I'm thinking about a horizontal shift, same way with a vertical shift, we're looking for something being added or subtracted, but this time it's happening inside the parentheses. So our original function for transformations is A is times f of bx minus h plus k, where A and k happen to be your vertical transformations. F doesn't really do anything other than tells us it's a function. B happens when we're talking about a horizontal stretch or compression, and then H is this horizontal shift or translation. But if we look at this original function, since X is subtracting H in the original form, the way we think about it is going to be opposite of what we see, because when I'm subtracting H, it's going to change things a little bit, and I'll show you why. So let's say H is 3. If I plug in 3 in this little expression here, I would get f of x minus 3. That 3 is a positive 3, correct? Positive 3, we move right. Or f of x minus 3. That means I just took away these parentheses. Well, since it's a positive 3, I move right. But normally when I see subtraction, I'm moving left. But because the original form is already talking about subtraction, normally when I see subtraction, I move left. But since the original form is already talking about subtraction, I'm actually going to move to the right. because to be subtracting a positive 3, that means I still have subtraction. Whereas if this 3 was a negative, well, x minus a negative 3, two negatives would make a plus sign, so that when you see the plus sign here, it's actually going left. So here's an example. The linear parent function is f of x is equal to x, and g of x is equal to f of x minus 2. The first thing I notice is that x is being subtracted by 2, or x is subtracting 2 inside the parentheses. Inside the parentheses, I'm adding or subtracting. That's automatically a horizontal shift. The next thing I need to decide is which way I'm going. Well, horizontal, think opposite. Normally, when I'm subtracting 2, I think I'm moving to the left. But horizontal, it's inside the parentheses. We're going to think the opposite. So this is actually moving right 2. This example, I have g of x is equal to f of x plus 2. Again, inside the parentheses, I'm adding or subtracting. It's a horizontal shift. And horizontal, we think opposite. So normally when I add 2 on the horizontal, I move to the right. But instead, this time I'm going to move to the left. All right, a horizontal stretch, again, it happens inside the parentheses, but a horizontal stretch occurs when a number is x is multiplied between 0 and 1, with a number between 0 and 1 inside the parentheses. Now, if you'll remember, when it was outside the parentheses, if I was multiplying by a number between 0 and 1, that was actually a compression. So like I said before, horizontal is the opposite way of thinking. So this time, if I'm multiplying between 0 and 1, it's going to be a stretch. It's the opposite of what we would do for vertical. So again, linear parent function is f of x is equal to x. And this example, I have g of x is equal to f times 0.5x. It's inside the parentheses, so you're automatically thinking horizontal. It's multiplying. As soon as you determine it's multiplying, you have two choices. It's either a stretch or a compression. And since it's inside the parentheses, it's the opposite way of thinking. Normally, if I'm multiplying by a number between 0 and 1, it's actually going to be a compression. So since it's opposite, it's going to be a stretch. Same thing here, 3/4 between 0 and 1, it's going to be a stretch. Now, moving on with our trend for an opposite. Oh, wow, I'm just making all kinds of typos today. This is a horizontal compression because we just did a stretch. Horizontal compression. If I could even spell. That's why I teach math, you guys. Horizontal compression. Again, it's when x is multiplied by a number greater than 1. Wow, just making all kinds of mistakes. This is what happens when you duplicate your slides. You just want to make sure you get everything done, unlike I did today. So a horizontal compression, it's when it's inside the parentheses and I multiply by a number greater than 1. If I'm inside the parentheses, it's automatically horizontal, and horizontal is the opposite way of thinking. So the linear parent function is f of x is equal to x. And my example here is g of x is equal to f of 3 of x. It's inside the parentheses. I'm immediately thinking it's horizontal. I'm multiplying. I have two choices. It's a compression or a stretch. Now, normally when I multiply by a number greater than 1, it's going to be a stretch. So since horizontal is all about opposites, it's actually a compression. Same thing here. 1.5 is greater than 1, so therefore it is a compression. All right, last one, reflection over the y-axis. The reflection over the y-axis occurs when you multiply by a negative inside the parentheses. So if I'm inside the parentheses and you see a negative sign, it is a reflection over the y. If the negative sign is outside the parentheses, it's a reflection over the x. And like I said earlier, the negative just tells you the reflection. So after I've seen the negative is inside the parentheses, I know it's a reflection over the y. I can actually cover that negative up and then determine whether it's a stretch or compression just by the number. So for this example, I would cover that negative up. I see it's a 3 I'm multiplying by. It's inside the parentheses, so it's horizontal. I know I'm multiplying, therefore my options are a stretch or a compression. And since it's opposite day, normally I would say a number greater than 1 is a stretch. So in the horizontal case, that would be a reflection over the y-axis and a horizontal compression. All right, ladies and gentlemen, hopefully this helped review some of the linear transformations for you. Please let me know if you have any other questions.